Okay, day 4, Physics 210. We have taken our information from our previous kinematics equations from the first 2 days. We are adding the whole idea of two-dimensional space that we somewhat explored in day 3. And all we're really doing is we're putting the two together. So what we're given is we're told that a field goal is being kicked from 35 yards away. So it's actually something like the 32-yard line, technically, because the end zone itself is 9 yards away. So we've got 35, 30, 25, 20, 15, 10, 5. So, and we're kicking from right here. We've got our football. And we're trying to make it into our field goal, which is going to be right here. So our kick is going to go something like this, and we're hoping to get it in. We are told that we are initially moving with a velocity of 26 meters per second. So V0 is equal to 26 meters per second at an angle of 40 degrees off the ground. So the kick is such that this is 40 degrees off the ground. We are asked for, so I'm going to put what to find. Yep, my what to finds are, I want to know, one, maximum height. So I'm going to call this point, so this was point 0, so this is going to be point 1. So we want to know y at 1, or y1. I should probably use that. That's better symbology. So we want to know y1. We want to know distance the football travels. So we want to know delta x. So we're just going to call it, sorry, distance the football travels. So let's just do this. So x, and we're going to call this, how do I have these labeled? This is going to be 2, x2, and we want to know, will it make it? Which the information we have for that is that our goalpost is, got a different thing in my picture versus my notes, but I think it is 9 meters tall. Let me double check your, it says the bottom of the crossbar is 3 meters off the ground. I have, so if it'll make it through that piece. And for that, we're testing right here, which is going to be position 3. And we can actually do that in 2 different ways, which we're going to see in a second here. So, first piece, let's talk about this maximum height 1. What we're going to do is what we were doing for class for day 3. And that is, we want to make sure that we are considering everything separately for the x-axis versus the y-axis. And those are off the screen, I apologize. For the x-axis versus the y-axis. Perfect. Okay. What do I have? I have we're going to be adding a ton to this no area as we break it out. But I have my velocity at 0 is 26 meters per second. And we have theta at 0 is 40 degrees. We have, this might be what we call 3, but we have my y. It's not describing the ball, so I'm going to leave that 3 meters out of there because this is what I know about, we're going to call this what I know about the ball. Because that's what's moving in this. And the other piece I know is that gravity, acceleration is just that of gravity, which is negative 9.81 meters per second squared. And the reason I'm putting negative is what I'm going to do is I'm going to call this direction positive x, because that's downfield, and up is going to be positive y, because normally it's really nice to have up being positive. It gets confusing otherwise. Okay, so, well, in order to do anything else, I can't work with this v naught as it is. I need components that are either in the x or in the y, because those two pieces are going to work separately. The only thing that's going to go between those two is my time. Time is going to be what's connecting these two different sides of my chart here. So, in order to get my velocity in the x, I'm going to go ahead and draw my kick here. This portion is my x. This portion is my y. And I'm going 26 meters per second. And this is 40 degrees. Okay? So if I want my y, that is going to be velocity naught in the y is going to be equal to 26 times this is opposite, so this is going to be sine. Don't get too comfortable with, oh, y is always sine, x is always cosine. I could also give you something where I give you this angle. If I said this angle was 60 degrees, then my y is going to be cosine, my x is going to be sine. I think that is something that commonly happens. People don't draw out the triangles and they just assume that y is always sine, x is always cosine. That will not always work for you. So y is opposite, so sine 40 degrees. And that means that velocity in the x initial is going to be 26 times cosine of 40 degrees. Perfect. Velocity x is going to come out to 19.917 meters per second, and that is going downfield. That's positive. We're still good there. And in the y is going to come out to 16.712 meters per second. And that is going up, so we're still good there. Perfect. First question, how high am I getting? Well, there are a couple ways to do this. I know that I've been telling you that I always like to go ahead and use my two equations. So we're in kinematics now. I should say, let's make a comment. Acceleration is only in the y, because gravity doesn't go up or down the field. Otherwise, one side of the football field would be a huge advantage over the other. With that, sorry about the distraction. We have our kinematic equations. We have x final is equal to x initial plus v initial times time plus 1/2 acceleration times time squared. This is acceleration in the x, because we're talking about the x. I could write the same thing out. Y final is equal to y initial plus, this is velocity initial in the x, this is velocity initial in the y, times time plus 1/2 acceleration in the y times time squared. And then I have my velocity final in the x is equal to my velocity initial in the x plus acceleration in the x times time. I can say the same thing, velocity in the final in the y is equal to velocity initial in the y plus acceleration in the y times time. It's really, these equations are the same equation, these equations are the same equation. It's just whether I'm talking about it on this side or on this side. And then the last one that we can use, sorry for erasing a bunch of these. I'm going to go ahead and write them out without the two different specifications. X final is equal to x initial plus velocity in the x, initial in the x times time plus 1/2 acceleration in the x times time squared. Velocity in the velocity final in the x is equal to velocity initial in the x plus acceleration times time, acceleration in the x. And then the last one, velocity final in the x squared is equal to velocity initial in the x squared plus 2a in the x final minus x initial. Whew. So those are my three kinematic equations from day 2. And those are what I'm going to be using to solve these pieces. So I want y1. Ignoring the fact that I wrote this down with x's, I have, if I go between 0 and 1, I could say that this is y1, this is y0, which I have. This is velocity, oh, sorry, y0 is going to be 0. It's on the ground. Y0 is 0, x0, we're just going to call 0. I know it's on the 32-yard line, we're going negative. We're just going to call the initial point 0. So y final, we want the height at 1. That is what we're solving for. Y1, that's y0, which we know is 0. We're starting on the ground. We have velocity y initial, so velocity 0 in the y, which we have right there. We have time, we do not have. 1/2 is a constant. Acceleration in the y, that is going to be our gravitational acceleration, time squared. So we could solve this value in order to get, actually we cannot solve this because we do not have the final height, we do not have the time. We have velocity final in the y, which we know actually, because this is the top, velocity at 1 in the y should be 0. Because when you hit the maximum height, it's going to start going down. So we define this point by the highest point. That should be 0. So we have velocity final in the y, velocity initial in the y, we have right here. Acceleration in the y, we have right there. Time, we could solve for. So what we can do is we can use this guy to solve for our time. We can then plug that in up here and we can solve for our maximum height. Or we can use this other equation. Velocity final in the y is 0. Velocity initial in the y is right here. Acceleration in the y is right there. We want the final height. We subtract the initial height, which is 0. So we can use this guy. If we wanted to, in my notes, I used the other way. So I'm actually going to use these two just because they're what I am most comfortable with. So what I'm going to do is I'm going to work with the y here, and I'm going to say velocity at 1 in the y is going to be equal to velocity at 0 in the y plus acceleration in the y times my time. Velocity at 1 in the y is 0. Velocity at 0 in the y is 16.712. Acceleration is negative 9.81 times time. This is in meters per second. This is in meters per second squared. Time comes out to be in seconds. And I will figure out from this that my time from 0 to 1 is going to be 1.704 seconds. And there is actually a reason I'm doing this here, because we will want this time later. So we're going to add this to the stuff I know, because this is going to have to constantly be erased. So time 0 to 1 is 1.704 seconds. Perfect. And then I can figure out, I can say y at 1 is going to be equal to y at 0 plus velocity at 0 in the y times my time plus 1/2 my acceleration in the y times my time squared. I want this y1, that's what I'm solving for. y0 is 0. Velocity initial is going to be this 16.712 meters per second. That is going to be multiplied by my 1.704 seconds. Meters per second times seconds is just going to be in seconds, plus 1/2 times my acceleration, which is negative 9.81 meters per second squared, times my time squared, so 1.704 seconds squared. Meters per second squared times seconds squared is just going to come out to meters. And I can find that my final height, y1, comes out to be 14.236 meters. So it is going up 14 meters in the air. And do I have space? 14.236 meters. Whew. Okay. That is my first piece. Now I have to find where it hits the ground. How far does it actually travel? Hopefully it is more than the 39 meters, 35 meters, 41 meters. I'm kicking from the 35. Whoops. I think I said something in the beginning because I misread it. The distance here should be 41 meters. 35-yard line, a 32-yard line plus 9 meters away. We're going to double check that, that I've got all this right in my notes in a second. I think I misread the question there. I've got to go 41 meters. That's the important thing. And on the question, I have 41 meters. Okay. We are all set there. Okay. 14.236 meters is our height. We want to know x2. So in order to get that, none of this, well, the only thing that can currently come over is I can figure out what time I can move time 1 over here. I don't really care about x at time 1. I don't care how far it's gone when it hits its peak. I care what time it is when it hits the ground. So what I'm going to do here is I am going to see how long it takes to hit the ground. And there is a shortcut to this that I think we may have already talked about, but I'm going to do it by hand one more time before I assume that you can take this shortcut. So we are going to say that y2 is going to be equal to y at 1 plus velocity at 1 in the y times the time plus the plus 1/2 times the acceleration in the y times time squared. y2, I know that I'm talking about when it's hitting the ground, so y2 is 0. y1, and that's something that I probably should have had over here. Keeping track of all my variables. y1 is 14.236 meters. I'm sorry, I'm going to start getting rid of units just because of the space on this board. I would not recommend doing it in your notes. Velocity 1 in the y. Well, at the very peak, we said velocity 1 in the y is 0. So that is 0 plus 1/2 acceleration in the y is negative 9.81 meters per second squared times the time squared. So we end up with time between 1 and 2 is going to be equal to the square root of negative, because I got to move it over, 14.236 divided by 1/2 times negative 9.81. This is in meters. This is in meters per second squared. We end up with seconds squared. Take the square root of that. We should end up with seconds. So our units are all working out. And I get 1.704. That looks familiar. That was the time from 1 to 2. When it's just gravity acting on something, you've got a constant acceleration. The time it takes to go up from 0 is the time it's going to take to go back down. So our total time from 0 to 2 is going to be equal to 1.704 seconds, so that's the time from 0 to 1, plus 1.704 seconds. I don't know why I've got seconds on one and not the other, which is time of 1 to 2. So time from 0 to 2 is going to be equal to 3.408 seconds. And it turns out that my 1.704 is rounding because this is 3.407 seconds if you don't round at all. So I'll go ahead and add that little tidbit over here. T0 to 2 is 3.407. You don't have to do all this. This is just me because I'm going to be erasing so much of this board, keeping track of everything for myself. And we said that time is the one thing that can go over this great barrier. So I now have the time from 0 to 2, which is great because I can say that I want to know what this x2 is. Where is the position where it hits the ground? x2 is going to be equal to x0, which I have as 0, plus velocity initial in the x, which is 19.917, times my time from 0 to 2, because I'm working between 0 and 2 here. So that time is 3.407 seconds. plus 1/2 acceleration in the x times time from 0 to 2 squared. Well, what is my acceleration in the x? It's 0, because the only acceleration I have, there's nothing else going on here. The only acceleration is downward. So this guy comes out to 0. So my position when it hits the ground is just 19.917 times my initial velocity. Oh, sorry, times that's my initial velocity times my time, which is 3.407 seconds, which is going to come out to 67.862 meters. So it is going 67.862 meters. I figured out what it was. I'm talking about 35 yard lines. I converted yards to meters. That's why it's 41. Took me a second, I'm sorry. This guy comes out to 67.862 meters. Those are the two easy ones that we have solved now. We know that it is going to reach a maximum height of 14.236 meters. We know that it will hit the ground after going 67.862 meters. What we don't know is how, whether or not it's going to go through the goalpost, because we know it's way higher than the goalpost here. We know that it is on the ground here. We need to know where it is when it passes this 41 meter mark. Got two ways that we can do that. The first way is going to be to work in the x first. I know, and I'm going to go ahead and leave that one up there. I know that I am going 19.917 meters per second in the x. And that is constant because it's not changing. So I can throw up this equation for position 3, and I can say that position 3, in this case, is at 41 meters. So that is my definition of position 3 in this case. It'll be different in the second way to solve this, so bear with me there. So my at time, what I'm going to do is I'm going to say at x3 is going to be equal to x0 plus v0 in the x times t plus 1/2 acceleration in the x times t squared. Well, acceleration in the x is 0, so that goes away. And my x initial is 0, so that goes away. So my x at 3 is going to be, x at 3 is v naught x times t. I know my x at 3 because we defined that as 41 meters, is going to be equal to my velocity in the x initial, which is 19.917 meters per second times my time. So I can say that my time is going to be equal to 2.059 seconds. And why do I need that time? Because that time is the one piece that I can bring across this barrier. I know that I want to know what's happening at a time of 2.059 seconds. And if at 2.059 seconds I am higher than 3 meters, then I'm going through the goalpost. If I am lower than 3 meters, I am going under the goalpost. If I'm at 3 meters, we get the nice ping of the football bouncing off the goalpost. So with that, what I'm going to do is I am going to say that y3 is going to be equal to y0 plus v naught in the y times t plus 1/2 times my acceleration in the y times my time squared. And I have all of this. So y3 is what I want to know. Is it higher than the goalpost? I can say y0, it's being kicked off the ground. y0 is right there is 0. Plus v naught in the y, which was what I solved for way back when up there, and ruh-roh, I didn't move it over here. V naught in the y was 16.712 meters per second. I'm going to multiply that by my time, which is coming from right here, 2.059 seconds. And then add 1/2 my acceleration of gravity, negative 9.81 meters per second squared, times my time squared, 2.059 seconds squared. You guys can't quite see the squared. There we go. That gives me y3 of 13.617 meters. That means it is 13 meters up when it goes through the goalpost. It is way over that goalpost. That is absolutely no problem. So yes, it does make it. Okay. That is not how you have to solve it. There are actually two paths here. So the first path we just did was asking ourselves, how high is it when it reaches the goalpost? And that height, we determined, was higher than the bottom of the goalpost, which meant it went through. The other way we can do it is we can figure out how long until it drops to 3 meters, at which point we can go ahead and determine how far it's gone. And if it's gone past the goalpost at that time, we're all set. We have gone far enough. So with that, what that's going to do is instead of starting in the x, we're going to start in the y. And we're going to say y3, this is at y3 is equal to 3 meters, is how we're going to define that. So this is a completely different 3. We could, in fact, what we're going to do, just to save a little bit of confusion, is we're going to call this 0.4. And that is defined as y4 is equal to 3 meters in height. Ooh. And I have this, I might have to pull out a calculator here because I solved this with a 9 meter tall goalpost instead of a 3 meter tall goalpost. So slight typo there that happened at some point. It still makes it through the 9 meter tall goalpost, so same answer, but y4 is going to be equal to y0 plus v naught in the y plus 1/2 at squared is what we could, is one way to do this. This is not quite going to be how we want to do it, because when we solve this, we get y4, we know y4. We get a 3 meters is going to be equal to 0 plus 16, correct? 16.712 times my time, which I'm solving for, plus 1/2 negative 9.81 meters per second squared. I don't know why I'm doing units on some and not on others, but times time squared. Yikes. This is quadratic formula area. And I told you guys didn't have to do quadratic formula anymore. So let's not do it that way. What we're going to do instead is we have this lovely high point. So we can find the difference between 4 and 1. So we can say that 3 meters is going to be this high point, so 14.236 meters, plus velocity 1 in the y is 0, so that goes away. And we don't have a single t and a squared t, plus 1/2 times negative 9.81 times t squared. And I can solve that for t, no problem. Or I could. I just need to pull out a calculator here. So I have t squared is going to be equal to 3 minus 14.236 divided by 1/2 times negative 9.81. And to get rid of this square, I have to take a square root. So 3 minus 14.236 times 2 divided by negative 9.81. Square root of that is going to give me a time of 514, really. 514 seconds. Okay, with that, 1.514, that is not my total time. That is the time from here to here. So I'm going to have to add on my 1.704. And that is going to give me a total time of 3.218 seconds. That guy can move across the line. It is a time. And I can say that x at 4 is equal to x naught plus v naught in the x times t plus 1/2 a in the x times t squared. I know that this is 0. I know that this is 0. So I am left with x4 is equal to that v naught x, which is 19.917 meters per second times 3.218 seconds. Is going to give me a distance of 64.083 meters. So it goes 64.083 meters before it sinks below the 3-meter high board. That is well past said board, and we are all set. I apologize if this guy changes to 9 meters. There is a chance this will change to 9 meters. That is what I have in my answer key. I will double check on it, and we will work it out with that on the rubric. But solving it, exactly the same thing. This is just the potential mistake. Take care.